All right, so our next thing that we're going to look at are rational exponents. So hopefully we recall that rational numbers mean that it can be written as a fraction. So when I see rational exponents, I'm thinking of fractional exponents. So if we have something that is written with a base of a, and we have m divided by n in our exponent, so that whole fraction is in our exponent, we can rewrite that using a radical instead of an exponent. So remember that the n becomes our index. So my a is what's going to be the radicand, because that's what's underneath my radical. The n becomes our index, and our m becomes our exponent. So an example of this would be if we had x to the 2/3, we could rewrite this as the third root of x squared. So the bottom number will always become my index. The top number becomes my exponent. So again, we have some properties with this. So one of those first properties, notice, is that if we were to rewrite this as the nth root as a to the m, we can also bring that m power out. So like on this example, we have the third root of 8 squared. We could go ahead and square that 8 first and get 64. Or instead, we could take that squared out to the outside, take the third root first, and get 2. So sometimes, depending on how big a number is going to be, it can be helpful to take the root first and then apply that exponent. On property number 2, we have the nth root of a times the nth root of b. So again, as long as we have the same value here, or the same index, we can apply those to be underneath the same radical. So in the example, we have the square root of 5 times the square root of 7. Because they both have an understood index of 2, we can put them under the same radical and get the square root of 35. A very similar property is if it looks the same, but it's division instead, we can divide those two things underneath the same radical. And like the example, we would just combine them and get 3 in that case. The biggest thing to be careful about is that b value, or that bottom value, cannot be 1, because remember that, cannot be 0, because we cannot divide by 0. On our next property, if we have a root within a root, we can actually just multiply those two indexes together, and we get the n times nth root of a. So in this example, we have a third root, an understood square root. 3 times 2 gives us the 6th root of 10. Next up, hopefully we recall from Algebra 2 that radicals and exponents are inverses of one another. So that means that if I have an exponent of n and a nth root radical, they are going to multiply together and undo each other. So we just end up with whatever is underneath our radical. And then lastly, if we have an even index, remember that we do need to look at the absolute value of whatever it is that is underneath our radical, because we want to make sure that it works out correctly. So we always want to apply that absolute value. If n is odd, then we want to leave that negative in place. So like in this case, it would be the third root of negative 12 to the third would give us negative 12. So let's look at some examples. So simplifying even roots. So notice that we have the fourth root of 48. Now, I don't know if we just off the bat know our fourth roots. If we don't, then remember that we can always make a factor tree. Some people also rate it as like a factor chart. I've also seen factor cakes. Whatever method works best for you is fine. I tend to use the factor tree, and that's just what's easiest for me. So if we have 48, to split it up into factors, we're looking for prime factors. And usually we're going to start with a 2 or a 3, depending on what can be divided out. So for 48, it isn't even, so we know that 2 is going to go into that. So we get 2. If we divide 48 by 2, we get 24. Well, 24 is not a prime factor, so we know that we can look at the factors of 24. So we get 2. And dividing 24 by 2, we get 12. Again, 12 is not prime, so we're looking at the factors of that. We get 3 and 4. And then lastly, 4 can be divided into 2 and 2. So because we're looking at a fourth root, remember that we know that exponents and roots are inverses. And so we want to try and find something that can be written as the fourth power, which means that we're trying to find 4 things multiplied together. So if we notice, I have 1, 2, 3, 4 2's. So that can be rewritten as 2 to the 4th. And notice that we have a 3 left over. So that 3 can't just be left out. We would have to multiply by 3. And that's going to be helpful because if we rewrite this now as 2 to the 4th times 3, we can break that apart into 2 separate radicals using those properties that we had on the previous page. So as long as we keep our indexes the same, we can split it apart. So we have the 4th root of 2 to the 4th. And the reason that we want to do that is because now my 4th root and my 4th power are going to reduce each other. So we have a 2, and then that 4th root of 3 cannot be simplified anymore. So it's just going to be left as 2 times the 4th root of 3. Now, for our next problem, we add in some variables, which is fine. The process is going to work the same. So again, if we didn't know what the square root of 75 was, which there's not one, we would want to look at our factor tree. So if I look at 75, we know that 25 can go into 75 3 times. And then hopefully we recognize that 25 is a perfect square, so that's going to be 5 times 5. And the reason we want to do that again is because then I have 2 5's and a leftover 3. So we can rewrite 75 as 5 squared times 3. Now, notice we also have an x cubed. So very similarly to like what we've been doing, we want to write that as something squared, and then we're just going to multiply by whatever's left over. So if I have an x to the 3rd, and I want to break apart that x squared, I would have an x left over. And we want to do that because now I have the square root of 5 squared times 3 times x squared times x. So notice we could break it apart just like we did in our first example, but just to save us a little bit of space, notice that that 5 would reduce with my square root, so it's going to come out to the front. And this first x squared would reduce. So it's going to come out to the front. And we're left with a square root of 3x. Now, because we have a square root, we need to put absolute values around it, whatever we bring to the front. So we would have 5 times the absolute value of the square root, times the square root of 3x. Now, in our last example, hopefully we noticed that we have a fourth root and a fourth power, so those two things are going to reduce one another. The important thing is going to be, because 4 is an even number, we need to put absolute values around it. Now, you could go ahead and write absolute values around the whole thing, but hopefully we know that 5 is positive, so it is kind of redundant to leave it in the absolute value, so we could go ahead and multiply and just say it's 5 times the absolute value of x. All right, so next up, we are going to be rationalizing. So hopefully we recall that roots are irrational numbers. And if we want to rationalize the denominator, basically that means that we want to take an irrational number and get it out of the denominator, or make it rational. So in our first example, we have 5 divided by 2 times the square root of 3. So hopefully we recall that if I have a square root, the way that we rationalize that is to multiply the top and the bottom by whatever that square root is. And we're allowed to do that because the square root of 3 divided by the square root of 3 is just 1. So we're not changing the value of our fraction, we're just changing the way that it looks. So if we notice, we would have 5 times the square root of 3. And then we have 2 times, because we now have 2 square roots of 3, we would have the square root of 3 squared. And because our radicals and our exponents are inverses, they're going to undo each other. So I'm left with a 5 times the square root of 3 on top. That 3 is going to be left by itself, but because it is still being multiplied, we have 2 times 3, so we get a 6 in our denominator. Now, if we could simplify those numbers any farther, we would, but 5/6 is already as simple as it can get. So that would be our final answer. Now, part B is a little bit different. So notice that this time we have a third root. And the reason that this is different is because if I just multiplied by the third root of 5 to the top and the bottom, like we did on the previous step, notice that the numerator would be fine. I would get 2 times the third root of 5. But now I have 1, 2 third roots. So I have the third root of 5 squared. But the problem is because my index is not 2 this time, if I have that squared, that exponent and that root aren't going to reduce each other. So it didn't do me any good to just multiply by what we had there. So if we notice, in order to make this exponent the same, we need to look at, well, what is my exponent that I already have? Well, it's going to be 1. What's the exponent that I need to get? Well, it's going to be 3. So what does this exponent need to be in order to get there? So we would do 3 minus 1 gives us 2 instead. So we would have 5 squared. We can either write the squared underneath our radical, or we can write it to the outside. So remember that property says that we can write it on the inside or the outside of our radical. So now we need to add in our squares. So that's going to make this number a 3 now instead, because now I have 1, 2, 3 third roots of 5, which gives me 3. And the reason we want that is because now that my exponent and my index are the same, they reduce one another. So we end up with 2 times the third root of, and we're going to go ahead and simplify that. 5 squared is going to be 25 divided by 5. Again, we check our numbers. We have 2/5. That does not reduce. I look at 25. I know that that's 5 times 5, so I don't have any groups of 3, so we can't reduce that radical on top either. So kind of a general way that we can write this is if we're looking at a denominator of the nth root of a to the m power, we need to multiply not just by the same thing. We're going to multiply the top and the bottom by the nth root, so that's going to stay the same. But just like we did here, we took my index and subtracted what exponent I already had. So we did 3 minus 1 gave us 2. So here my index is n, my exponent is m, so I would do n minus m. And that's going to give me the correct exponent, so that way our index and our exponents reduce. And that will work for any index, whether we have an index of 3 like we did here, an index of 25, which hopefully we never see a problem like that, but that rule will work no matter what the index is. Alright, now looking at our next one, I have 2 divided by 3 plus the square root of 7. So if we look at that, we do have a square root, but be careful, because if we just multiplied by the square root, we would be okay on top. We would end up with 2. So if we just multiplied by the square root of 7, we would end up with 2 square roots of 7. But then on bottom, we would have to distribute that square root of 7. So we would get 3 times the square root of 7 plus 7. So my square root of 7 reduced for my second term, but it didn't reduce for my first term. So it didn't help me a whole lot. So instead of doing that, we want to multiply by a different expression. We want to multiply by the conjugate. So hopefully we remember from Algebra 2. If we don't, here's our refresher. Anytime that I have a plus the square root of b, the conjugate is going to be a minus the square root of b. And vice versa. If I have a minus the square root of b, then the conjugate would be a plus the square root of b. And that's what we want to multiply by instead. So we have 2 divided by 3 plus the square root of 7. Our conjugate would be 3 minus the square root of 7. And it's going to work like magic. Our irrational number, or that square root of 7, is going to disappear from our denominator, which is what we want to happen because we're rationalizing that bottom or that denominator. So when we multiply the top, so notice that we would have to distribute our 2. So we would do 2 times the whole thing. So we're going to leave it like that for right now, just to make sure that nothing simplifies. In the end, if it doesn't simplify, then we'll go ahead and distribute. Now, on our denominator, notice that we have a binomial, or 2 terms, times another binomial, or 2 terms. So I'm going to go over here to the side and do a little scratch work. So I have 3 plus the square root of 7 times 3 minus the square root of 7. So we need to first do 3 times 3, which gives us 9. Then we need to do 3 times negative square root of 7, which gives us a minus 3 square roots of 7. So then we want to do the square root of 7 times 3, which gives us a positive 3 square roots of 7. And then lastly, we want to do square root of 7 times a negative square root of 7. And that's going to give us just a negative square root of 7 squared. Well, if we notice that negative square root of 7 squared, those are going to reduce each other. And if we notice, I have a negative 3 square roots of 7 and a positive 3 square roots of 7. So those are also going to reduce each other to 0. So those are going to go to 0. My square root of 7 and my 2 reduce as well. So we're just left with 9 minus 7. And 9 minus 7 is going to give us 2. So now, because I did my scratch work on the side, it makes it a little bit easier up top. I'm just going to replace, so I multiplied these two together, and I got 2, so that's what's going to go into my work. And lucky for us, now notice that we have a 2 up top and on bottom, so those are going to reduce to 1, and we're just left with 3 minus the square root of 7. Our denominator here is now technically 1, which is a rational number, so we did indeed rationalize the denominator like it asked us to do. So that would be our final answer. Alright, on this one we're just changing from radical to exponential form. So notice that we have a square root of 3. If there is no index, hopefully we recall that it is an understood index of 2. We don't have an exponent on the 3, so it's an understood exponent of 1. So we end up with 3 to the 1/2. On our next one, we also have a square root, but this time we have a 5th power. So when we rewrite it, we would have 3x y to the 5/2 power. Now it's important that we do leave that parentheses there because notice that the 3xy is all to the 5th power. If that 5 was just to the y, so note. If instead we had something that looks like the square root of 3x y to the 5th, this would become 3 to the 1/2, x to the 1/2, y to the 5/2. Or you could rewrite it as 3x to the 1/2 times y to the 5/2. So that y is the only thing that has the 5th power with it. In this case, because there's the parentheses, the whole thing is being applied, so we do need to leave those parentheses there. Now on our next one, hopefully we notice that I have an x on the outside and an x on the inside. Right now, because we have a radical, we can't simplify that. However, if we were to rewrite that in exponential form, we would get 2x times x to the 3/4 power. Now that's important because now notice that we have two things that have the same base. They both have exponents. One of them happens to be a fractional exponent, but we can still use our exponent rules. So instead of just having x times x to the 3/4, I'm going to add those exponents together. So we have 1 plus 3/4. And hopefully we remember, in order to add a number and a fraction, we would need to find a common denominator. Since it's 1, it's just going to be 4/4. So 4/4 plus 3/4 gives us 7/4. So now it looks a little bit nicer. We only have one x instead of having two and them being separated. And so that would be my final answer. If for some reason here we say we got like an 8 instead of a 7, we would want to simplify that, and that would be 8 divided by 4, which would give us x squared. In this case, 7/4 does not simplify, so that's just our answer. Alright, last up, simplifying with a little bit more complicated exponents, but that's okay. So on our first example, we have negative 32 to the negative 4/5 power. So we do have a negative, and that's okay. There are two different ways that we can approach this. So the first would be if we just wanted to rewrite it in radical form, we could, but we've looked at some things like that, so we're going to go ahead and maybe look at it a different way. So I want to make a factor tree for 32. So hopefully we notice that 32 is an even number, so we can divide that by 2. So 2 is going to be one of our factors, and 16 would be our other factor. Again, 16 is even, so we end up with 2 and 8. Then we have 2 and 4 and 2 and 2. So remember that if I were to rewrite this 4/5 as a radical, I would have 32 to the 4th power, and it would be underneath the 5th root. Because we're looking at a 5th root, we're wanting to look for groups of 5. Well, notice I have 1, 2, 3, 4, 5 2's, which is helpful because that means that I can rewrite 32 as 2 to the 5th. But notice that that's a positive 2 to the 5th because I have a positive 32 there. But we do need to include our negative. So instead of negative 32, I would want to rewrite that as negative 2 to the 5th. Negative 4/5. And the reason we want to do that is because now, recall from our exponent rules, when we have a power raised to another power, we multiply those powers. Well, if we multiply 5 times negative 4/5, I have a 5 on my numerator and my denominator, so those are going to reduce. And we end up with just a negative 2 to the negative 4th power. And that's now helpful because that's a little bit easier to manage. Just giving me a little bit more room there. So now notice that we have a negative in our exponent, so we do need to make that into a fraction. So we would have 1 divided by negative 2 to the 4th power. And our last step would be to simplify. So if we took 2 to the 4th, we would end up with 16. And because it's an even exponent, it will become positive. So we just end up with 1/16. Now, some of you might be thinking, well, I just plugged that into my calculator and it gave me 1/16. That's great. because I just had a 32 there. So using your calculator would have worked. The problem would be is when we run into something that looks like B or E, where we have x's involved, we can't just plug that into our calculator. So we need to know how the process works, so that way whenever we have variables, we can reduce it the same way. Now, if something like part A showed up in any of your work, yes, I would expect you to plug it into our calculator. However, I still want us to know what those steps would look like. All right, so on our next one, notice that we have negative 5x to the 5/3 times 3x to the negative 3/4. I'm going to look at my numbers first. So I have a negative 5 times a positive 3. It's going to give me a negative 15. We have two things that have the same base, and they're being multiplied together. So we would end up adding those two things. So we have 5/3 plus a negative 3/4. I'm going to come over to the side and do a little scratch work. So we have 5/3 and it'll be minus 3/4. We need to find a common denominator. So our common denominator for 3 and 4 is going to be 12. So that means I need to multiply my first one by 4. So 4 times 5 gives me 20/12 minus, I need to multiply my second fraction by 3, which will give me 9 in my numerator. So we would get 9/12. So then subtracting, we do 20 minus 9 gives us 11/12. Now, plugging that into our problem, that negative 15 is going to stay the same. And now I have x to the 11/12. Again, if 11/12 reduced, like if I had 8/12, we would want to reduce that. But 11/12 doesn't, so that's going to be my final answer. Now, looking at part C, I have the 9th root of a to the 3rd. Now, looking at that in radical form, that does not simplify. However, if I were to switch that to a rational exponent, my 3 is my exponent, so it becomes my numerator. My 9 is my index, so it becomes my denominator. Well, now notice that I have 3/9, which can be simplified, so I would end up with a to the 1/3. Now, a good rule of thumb is if something is given to us in radical form, even if we switched it to rational form in order to simplify it, we want our answer to be in radical form. On the previous one, we were given things in exponential form, so we left them in exponent form for our answer. That can't be simplified any further, so the 3rd root of a is just our final answer. Now, I have the 3rd root of the square root of 125. So again, we could simplify this just using our radicals. However, we are practicing with rational. So we're going to go ahead and rewrite this. So 125, the square root of that, I would rewrite it as 125 to the 1/2 power. And then I have a 3rd root, so I would have the 1/3 power. Now, hopefully we notice that I have a power raised to another power, so we can multiply those powers. So I end up with 125 to the 1/6 power, which is a little bit more manageable. So now, if we wanted to go ahead and rewrite this, we would make a factor tree for 125. So 125 is odd, so we don't want to start with a 2, but we can hopefully notice that 5 goes into that 25 times. And then we have 25, which then 5 goes into that twice. So notice that we have 1, 2, 3 5s. So I know that I can rewrite 125 as 5 to the third. So rewriting that, I have 5 to the third to the 1/6. Again, using that same property, I have a power to another power. So I can rewrite that as 5 to the 3/6, which reduces. So we would get 5 to the 1/2 power. Now again, I was given something in radical form. Even though I switched it to exponential form, I need my final answer to be in radical form. So square root of 5 would be my final answer. Now, part E looks a little intimidating, but that doesn't mean that we can't handle it. We just kind of need to think through what our steps might be. So notice that 2x minus 1 is my base, and I have 2 of them. So that means that my bases are the same. So just like in part B, when my bases were x's, I added my exponents. Here, my bases are the same, so I'm going to add my exponents. So I would have 2x minus 1 to the 4/3 plus -1/3. Lucky for us, our bases for our fractions are already, our denominators for our fractions are already the same in our exponent. So 4/3 minus 1/3 gives us 3/3. Well, hopefully we all recognize that 3/3 is also equivalent to 1, so we just end up with 2x minus 1. And now that looks a lot nicer than what we started with. I don't have anything to simplify there, so 2x minus 1 would be our final answer.